I'm Dr. Gerson Rosenberg, professor of surgery and bioengineering and past president of ASAIO. Today I have the honor and the privilege of interviewing Kenneth Butler, pioneer in circulatory support. Ken, can you tell us a little bit about how you got interested in engineering and how your career developed?
Sure. And first of all, it's an honor and a privilege for me to participate in this interview. And I understand, considering all the other people that you've interviewed, it indeed is a personal honor, and I thank you. Going way back, I was born and raised in Vallejo, California, and I was the first person in my family to go to college. And I'd done in high school and junior college, I'd done quite well in science and math. And Vallejo is the home of Mare Island Naval Shipyard, which is one of the historical shipyards. And through my family's contact, who happened to be in the Navy, I was able to get a job as a summer intern on the Mare Island Shipyard, and I was able to participate in some design of nuclear submarines. That was the day. So it was a fascinating 3 years. I worked there every summer, even when I went to Cal. I was getting my engineering degree. And I got to go on the Nautilus and nuclear submarines. I got to watch several ships being launched, which is a great traditional Navy thing, and with the bands playing. And it was really a real heady experience. And it made me convinced that I did want to pursue a degree in mechanical engineering. So again, I did go to Berkeley, UC Berkeley, and graduated in 1961. And while at Berkeley, I took a couple of rocket propulsion classes, and I became interested in that. And I knew that right up the road, or up by Sacramento, there was this company called Aerojet Liquid Rocket Company. And so I got a job with them. That's where I started. So that started me on my engineering career in 1961. I was fortunate in that career at Aerojet to be working in some advanced development classes or groups, and it was in who employed several German scientists that came over from Piedemonte with von Braun's group, and these guys split off and came to work at Aerojet. And it was a fascinating experience to work with these rocket scientists, true rocket scientists who had been trained in Germany, had a lot of experience, and they taught me a lot about turbo machinery, about advanced liquid rocket propulsion design concepts, and I just really, really enjoyed that. And that was sort of the foundation of that went on, and I did a lot more work at Aerojet with different propulsion systems. I worked in solids, learned about heat transfer and ablative rockets. And one of the latter things I did at Aerojet was they had a program to develop a nuclear rocket that was to provide propulsion system to go to Mars. And it really was a nuclear rocket. And in those days, they didn't have any means of having radiation-hardened electronics to control the system. So we developed a fluidic system. And so I spent 2 years developing a fluidic temperature sensor, which was on an oscillator. Then the frequency was proportional to the square root of the temperature. And then I developed these fluidic circuits to modulate the signals and eventually come out with an analog signal that could be used to control the drum rotation on the nuclear rocket, thereby its radiation intensity and temperature. So that kind of set me up a little bit with experimental fluid mechanics. And I then learned Aerojet in the late 60s, it was late 60s, had some experimental programs funded by the Department of Energy to work on nuclear-powered thermal engines for space stations, space satellites. And if you recall, I think the first concept of an artificial heart, and I think Dr. DeBakey was one of them proposing that it be a nuclear-powered artificial heart. And Aerojet got a contract with, again, it was DOE, and then later in the early years to develop a nuclear-powered artificial heart. And we had developed a Stirling cycle engine that was powered by a 50-watt plutonium capsule, and we developed the actuators, and I think we teamed up with, I don't know, it was one of the early blood pump, and actually implanted these nuclear-powered hearts in calves, or cows, really, large cows, at the Texas Heart Institute. So when I came on board in 1973, that work had just been completed, but we still had the carryover of the artificial heart being a nuclear-powered device with, again, a Stirling cycle engine, pneumatic, magnetic coupling drive. And it was kind of fit in with all our aerospace background, because we were used to using, very sophisticated servo valves and hydraulic systems to control the liquid rockets. And heading up that artificial heart group was a guy named John Moise, who was one of the more brilliant PhDs at Aerojet at the time. And I knew him from some earlier work, and I had gone back in the early 70s and got a master's degree from the local university in mechanical engineering, but they had just started up a bioengineering curriculum. They had these young professors who were going to teach bioengineering. So in addition to my normal heat transfer and fluid mechanics courses, I enrolled and was taking biology and bioinstrumentation and those kinds of courses. So I ended up getting a master's degree in mechanical engineering, but with this heavy bioengineering curriculum as a sidebar. So that's what got me started. And John Moise called me over in 1973, and I went to work for him. And so that's how it all started.
So at that time, you really had no idea that you were going to be performing pioneering research that led to, the beginning of rotary blood pumps.
Absolutely not. I mean, we were really, again, because of our aerospace background, we were very successful in getting contracts, the device readiness contracts, and we had the pulsal devices with the electromechanical hydraulic system driven by a gear pump, and so we had and we were very successful in that endeavor. We had a contract to develop again a thermal powered artificial heart. We had another program to develop the device readiness programs, which was a completely implanted system, and we were quite successful, and so successful in that we could see that there wasn't going to be a future for this kind of work at Aerojet. They just weren't prepared to go all the way to work with the FDA and get approvals and all this stuff. So we said, why don't we form our own company? And it was about this time, I think in 1982, Barney Clark came along. There was a number of shifts. We were able to take the Aerojet contracts, and we formed Nimbus in those days. Nimbus Incorporated. There were 13 of us, broke away from Aerojet. I think there were several other groups had changes in those days too. So the timing was right. So we didn't leave Aerojet physically, but we resigned one Friday and came back the next Monday in our own little company in the same place and formed Nimbus Incorporated. It was led by John Moise. And we were successful with those contracts. And we're along the way, around in 1983, we got word from Sac State, where I'd gone to school, that there was this young doctor who was looking to do some consulting work. And so John, being who he is, he just jumped on it. He said, we got to get this guy. So we hired Rich Wampler as a consultant to us. And we were doing implant work at UC Davis at that time, and we really needed somebody who could bridge that gap between. Although I'd had the bioengineering degree, it wasn't that good in the surgery suite, and Rich was very comfortable and provided us with very valuable assistance in doing these animal studies, and you know how involved that can be. So we hired him as a consultant, and then he became part of Nimbus. Now, Nimbus had like 2 contracts with NIH, and it was the rule in those days, if you had government contracts, you had to devote a certain amount of your research to what they call R&D. So you had to take some of your profits that you had spent or were gaining from the contract and devote them to research and development. And Rich had this idea. I think you've heard the old sitting on the banks of the Nile story and looking at Archimedes' pump, of putting one of those things on the end of a catheter and an axial flow pump and having peripheral access. And he convinced John that that's what we should do. And John was a real visionary, and he said, yeah, let's do it. So we took our money that we had from the company, and again, we knew these guys from Aerojet who were turbopump experience, or really turbo machinery designers. One was a young designer named Paul Buckman, who was a genius mechanical designer. And another guy was Merle Huppert, who was like a 65-year-old engineer out of Rocketdyne who had loads and loads of pump experience. So we came up with a design input requirements sort of document. It said we needed to pump 3 liters per minute. We need to generate 120 millimeters mercury pressure rise across the pump. What is it going to look like? So we, every Friday, I think, for 6 or 8 months, we sat down and just blue skied, how are we going to do, what is it going to look like? And we would give the design task to Paul, who would go home and come out with these lovely pen and ink sketches of a little miniature pump. And he would draw the drawings at 10 times size, so they were very large. And eventually, we came up with what we thought may work. It was an axial flow device, axial flow pump. And in those days, we didn't have any CFD models. We didn't have any CNC machines. So we would look at the designs, and we'd pick 1 or 2, and we would start building them. And the way we would build the pump blade, the pump bodies, is the only thing we had was a pantograph, and we would make like 50 times sculptures of a channel, a blade channel, for one blade, second blade, and the channel in between. And we used, I think John did the basic design work from a hydrodynamics point, and he used a constant velocity or constant pressure, linear pressure rise across the channels. But that was the Bernoulli equation we used. And we made literally a sculpture. We used modeling clay in a 50 times size, put it on a pantograph, and the pantograph had a rotary head on it, and then we machined that down to a 10 times size. And then we took the 10 times size and made the final pump, which was, 1/4 inch in diameter, whatever the size it was. So we went through several iterations. And then along the way, we hired this young machinist. His name was Peter LeBlanc, who could build anything in any size, precision. So he would sit in on our meetings, and he would be the one who was charged to build it. Wampler was also heavily involved in doing the actual machining. And so we eventually worked our way to a hydraulic design that we thought might work. And produced, but it would take months or a month to turn to a different blade design, because we had to make a new sculpture, then we had to do the pantograph work all by hand, and then we had to do the polishing, and then Peter would do the machining of the bearings. And again, this was an axial flow pump, and as far as I know, it's never been used as a blood pump before. There was previous work by Perry Blackshear and Leonard Golding in centrifugal pumps, and we read all the literature of that, but we were charting new ground with this axial flow device. So that's how we sort of just drifted into it. And after about a year's worth of work on our own, and we again included HQ curves, hemolysis was somewhat new to us, and we ended up having our local slaughterhouse deliver us 5 gallons of bucket of blood every day, and we would treat it and filter it, and then we would run these hemolysis tests. And we would use the control, which was the Biomedica's BP80 was our control. So the control was, how did it do against the BP80? And the pump ended up being very much different than what we started out, because I was used to designing axial flow blood pumps that had 12-stage, or axial flow pumps that had 12 stages, and that was some of our initial designs were 3 stages, 4 stages, but eventually worked our way down to the minimum number. There was just 1 stage, and the minimum number of blades was 3, and that's the way that we evolved. It was just by trial and error in those days, and that's the only method that we had at our disposal at that time. So we worked like I said, we worked on it with our in-house funding, and then we were able to convince venture capital people that this was, because you looked at the numbers, the number of patients, and it was a very attractive venture group, and we had done enough in vitro studies, and we did do several in vivos. At that time, we had moved to a little place in Winters called BioSurge, and we did sheep in those days. So we did enough, and so we finally got a full venture capital funding to develop the hemopump. That was in 1984. We had some tough problems along the way, one of which was it was cable driven. It required a purge fluid to lubricate the bearings and the cable itself. And our first series of runs, we were running the pump, and it was pumped fine. The hemolysis would be fine, but after about 2 hours of running, the seals would clog up because of the debris that was being generated by the cable. We brought the coolant, which was it was sugar water, basically, and it plugged up the seals, and the bearings would seize. So we played with that for a while and butting our head against the wall, and finally, I think it was one day in my office, I remember it, on a Friday, we were sitting, I think we usually ended the month with a 6-pack of beer, trying to figure out what to do, and all of a sudden, it hit me and I think another guy named Barney Baxter that once said, hey, we're putting the fluid in at the wrong end. We need to put the fluid in at the pump end and pump backwards. And we prototyped that the next day, and that solved it. So we were off and running then. And then we grew up to like 60 people in the company, and of course the real challenge is how do you manufacture these things, and we know we couldn't keep making the blood components on a pantograph, and so we tried investment casting where we cast little sprues, and finally that worked. And were able to eventually get to a point where we did that first test in humans in, I think it was 1988, and you've all seen that famous picture of Bud and Rich Wampler and their patient, Dr. Kranick. And it created quite a stir. I remember the ASAIO meeting, it was up in Reno, and that's right after we had that first patient, and I was there, and I remember, whoa, this is really, things are starting to change now a little bit, and how much attention we got. Those were pretty heady days.
Yeah, that was really the beginning of axial flow pumps, and the DeBakey and Impella.
Right. I mean, yeah, that was the thing that broke it. As you know, the hemopump was never well, it was a clinical success. It never was a marketing success. And one of the things was that we royally underestimated the clinical regulatory environment we were getting into. And with a small company, venture capital, who wanted to make their money in a year or 2 years and get out, we didn't stand a chance, thinking back on it now. So we eventually, while it was a clinical success and technical success, it wasn't never a marketing success. And Nimbus gave the pneumopump to J&J, and they took it and ran at it for a couple of years, and they couldn't get through making a product, and they then sold it to Medtronics. So the last I heard was the hemopump was in some landfill somewhere out in Wisconsin, so it was just dropped. But what it did do was show the rest of the world that, hey, this can be done, and that just unleashed everything, from Jarvik to Dr. DeBakey to the guys in Vienna, and it changed. It literally changed the scope and the landscape in those days. So, in that it was a very success. And what it did for me and John and our group say, this is the future. We need to build on this technology. And going back, we had a pretty heady scientific board Nimbus did with the hemopump, and on that board was Bud Frazier, other guys, Wynn Phillips, and some of those guys, and we would meet with them every quarter. And we were about a couple of years into the project. We hadn't done our first clinical yet, and we were at a scientific board meeting. We had these board meetings in San Francisco in one of those, our lawyer's office, which overlooked the whole bay. It was an absolutely glorious day, and the sailboats were out. And we had gone over the progress, and Dr. Frazier was there, and he leaned back, he said, tell me, can you guys make this a little bigger, and so it'll flow 6 liters a minute, so that we can maybe think of a chronic system? And we said, sure, we can sure as hell try. So we did. John went back, and we did the scaling, went through the scaling laws, and said if it's going to pump 3 or 6 liters a minute, this is what the size should be. And it was a simple ratio. I think it came out the square root of 2 or something. So we built an exact version of it in a cable version. Again, a cable with a drive motor outside with purge seal and cable driven, and it ran a hemolysis test, and lo and behold, it produced the flow rate we want at the right speeds. It had lower hemolysis. We ran a couple in vivo tests over at Winters, and sure enough, yeah, it was worked. So the next thing we had to do was then get rid of the cable. So we did that. We kind of came up with an integrated pump motor version. So we were on our own. The hemopump was being pursued by Johnson & Johnson, J&J. So we relied on small SBIR programs to fund this. And we got a whole series of them and kept the work going. So we were able to develop an integrated motor, pump motor. We developed the integrated pump motor, all hermetically sealed. We were then started using this the very beginning of CNC machines, and we were able to do our own programming, modify our own little 3-axis, now 4-axis CNC. So we're able to produce these things. And we were able to use basic hemo technology, but it still had a seal and bearings. And so we required a purge fluid. And so we knew that was a real issue. But while I'm on the subject of SBIR, I want to say how important it was for NIH to fund these things through the SBIR path to keep this kind of work going. In fact, I think it was in 1990, there was a meeting of the Institute of Medicine in Washington, because at that time they were going to defund total heart programs. And I remember we all went back and testified before the committee saying, you know, this isn't really a good idea. And my job was to go tell the Nimbus sob story about how a little company who tried to do this through the venture capital funding and had a really killer project, but it wasn't a success because the quick turnaround time that the venture capital guys were looking for, and that it is absolutely vital that NIH keep pursuing this this technology through contracts. And at that meeting, I was approached after the meeting by Dr. Harvey Vorovitz and Dr. Griffith, about they were interested in our little axial flow pump and the potential it had. And so they funded us. They had a couple $100,000. So, and that we formed a partnership that was very fruitful as it was going to turn out with the kind of work we're able to do. So that's how it all kind of kicked off.
So that was the beginning of the HeartMate 2, is that correct? I mean,
Basically, yeah, that was the thing. Well, there was one more step that would need to be taken. And again, this was done under SBIR funded grants, they call them. We knew we had to get rid of the purge fluid. So we came up with this idea of putting a journal bearing on the outside diameter of the rotor at either end, and using blood and the natural fluid pumping action you get when you spin a cylinder inside a chamber to provide the bearing action. Well, so we built one, and we just simply took rings on either end of the rotor and stuck it in the motor stator and spun it up. And it worked great. It was very vibrant, vibration-free, very quiet, low power, but it hemolyzed every blood cell in the whole bucket. I mean, within record times. And so that was work. So, and also what it did was as you generated pressure, because the way the pressure balance goes, it forced the rotor out through the inlet of the pump. So to prevent that, we said, well, let's stick a bearing, a stop bearing, a little pivot bearing up at the inlet, and let's see if that solves the problem. Well, it solved the problem of the rotor moving, displacing out through the pump, but it still had very high hemolysis. However, it was only half the hemolysis that the other one had. So being the bright guys that we were, we said, well, let's put a bearing at the other end and see what happens. And so that's what we did. And it was, these were little spherical bearings. We had played with those on the hemopump, and thus was born the blood immersed bearing that was formed the heart of the key of the HeartMate 2. So we knew we were on to something. So we knew that it was important. Probably heat transfer at the bearing was very important. So to bracket that, what we did is we used bearing materials that consisted of tungsten carbide, which had very high thermal conductivity as one end, and we use I think it was alumina on the other end, on the other bracket, and it was very low thermal conductivity. We ran in vivo studies down at Pitt, and these were done at Pittsburgh, where Ken Litwack was doing them for us. And we, lo and behold, we discovered that the very high thermal conductivity material worked, and the very low conductivity material didn't work. There was a clot at the inlet bearing. So we said, okay, we got it bracketed. Now let's find what we can use, because we couldn't use tungsten carbide, and because it was of the biocompatibility. But we knew we had to find something. So we went through this extensive bearing material selection process. And about this time, the IVAS, the Innovative Ventricular Assist System contracts came along. And we were awarded one of those contracts. And that's how we did all that early bearing work on the IVAS contract, did lots of in vivo studies. And again, this was absolutely crucial. And one, I have to give credit to John Watson for sticking with us and being a big proponent of this kind of work. Without his support, we couldn't have done it. So we set up that's where we were. We had a successful in vivo studies. Again, our original IVAS was for a totally sealed system, so we had developed the TETs, the internal implantable battery. Fortunately, there was no compliance chamber, so that made it a little simpler, but so that was how we finished it off. The next thing that happened, this is a series of events. We were working on the total heart, as I mentioned, and I think you guys were involved. There were three of us. There were three of us, right? Yeah. And we were dropped out. I don't know why to this day, but we were. And I thought, wow, what are we going to do now? And by that time, I was leading the group. I was president of Nimbus. And I said, oh God, I don't know what I'm going to do. What are we going to do? So we got to work on this axial flow blood pump. I get a call from Vic Poirier. I think it was the day after we learned that we weren't going to get him. He says, are you interested in selling the company? Are you interested in coming with us? I said, sure. And then next day I got a call from Micromed, and they interested in merging with us. And so that was particularly interesting in my career, because we spent a whole day with Dr. DeBakey in our lab going over our version of this axial flow blood pump and discussing ways that we could merge. And I'll never forget, we had the opportunity to take Dr. DeBakey out to dinner that night. And you talk about dinner conversations. He could name drop with the best of them, from Marlene Dietrich to the Duke of Edinburgh. And so it was the most memorable night of my life, having a dinner talk with Dr. DeBakey. But we decided to go with Vic. And so we were in latter part December of 1995. I had the pleasure of, again, being up at that fancy conference room with our lawyers and our CFO, Joe Sullivan, waiting for a major check to hit our bank account from TCI, and that happened. And my wife went shopping at Union Square the next day. I remember that too, but it was those were pretty heady days. So we're merged with TCI. The next chapter in this story.
And that pump, I was going to ask you, what were the major hurdles in developing that pump? But at one point, didn't that pump then become textured like the heart?
Yeah. Okay. Well, I hope I don't embarrass Vic in this, but yeah, right after we joined TCI, Vic, who of course they had developed the HeartMate 1, and it had textured surfaces. When we joined TCI, we had the basic pump. We had the pump from the inlet fitting to the outlet fitting pretty much down. We knew what was wrong. We didn't have the inlet cannula design yet. We didn't have none of the peripheral equipment. You know, we could conduct a CAP experience. So joining TCI, we got the benefit of all the experience they had on the HeartMate 1 with the peripheral equipment. And of course, they had this experience with the textured surfaces, and which we really embraced as far as the cannula goes, the inlet elbows, the outlet elbows. So that was welcome. But Vic said, "Do you think you could texturize the interior of the pump?" I said, "What?" I said, "Yeah, it has a chance. If it works there in the HeartMate 1, what if we could build up an axial flow pump that doesn't require anticoagulants?" I said, "Well, that's certainly a noble goal. Well, let's try it." We knew we couldn't texturize the part that was spinning at 10 or 12,000 RPM. It just wasn't, and the clearances, but we could texturize both the inlet and the outlet stators. And we did that. I wasn't sure we could do it, but we did, and we did do it. And so the first pump, the HeartMate 2, had the textured inlet and outlet stators. And we did a series of in vivo tests, and we had mixed results. Sometimes it worked, sometimes it didn't work. So we talked to Kurt Dossie and Vic, and he said, "Well, that's the same experience we had on the HeartMate 1. So let's try it. We'll find out. We'll go into humans with it." So the first clinical that's what we did. I mean, we did do a trial one over in Israel, which was not a good result because the guy needed a right heart, and we weren't prepared to do all that. But we started out with the hemopump, or the HeartMate 2 in Europe, with a fully textured with inlet stator and outlet stator cannula. And I think we did like 10 patients, one of which was a spectacular success. It was done in England, and this guy had the pump in him for, I don't know, 4 months, and it just came out like perfect. But a lot of the others had thrombus at the inlet, on those inlet stators. So I remember at the time when we were looking at putting the texture into these inlet stators, I told Peter LeBlanc, who was the designer, I said, "Just make sure that we can take them off if we have to, because I don't feel good about this." And that's what it was. So we did eventually remove the textured surfaces from the stators, but the inlet canyon and outlet canyon still have the textured surfaces. And we went and did a whole series of in vivo studies, and eventually proved to ourselves that, yeah, this is what we're going to go with. And that's what started the HeartMate 2.
And that's now the most widely used blood pump in the world?
Yeah, I'm not exactly sure what the numbers are, but I think it's like over 20,000 things. Yeah, it's been kind of interesting to be a long-term attendee of these meetings, and back in the contractors meetings where we're telling you how we think it's going to work.
Yes.
To seeing that, my God, it actually does work. And so it's been a real heady experience for me, yeah.
Maybe you've sort of answered this, but if you had to pin down your biggest accomplishment, what would you think it would be? I mean, certainly a world leader in development of these pumps, but if it could be narrowed down to anything.
To what the thing that I like, I get the most high off of?
Sure, yes.
It was that when we were doing those experiments with the pump, with the nose going out, and we put the bearing on one end, it didn't work, and I said, "No, let's put the other one on the other end." And that's what we did, and I just thought, Jesus Christ, what? Am I lucky or what? It was just, we just stumbled on it. And the other thing we did, I have to admit, once we got the bearing materials identified, we developed a little test pump that had no vanes on the rotor, but it had a little disc in the that was mounted to the rotor so that we could spin the pump up and we could pressurize the disc and put loads on the bearing, because in the axial flow pump, the inlet bearing takes all the load. And so we were able to show with that little fixture that these bearings were indeed, they were hydrodynamic, because what we were able to do was to load the pumps, measure power, and then load the pressure so the front bearing was loaded, and we could run the pumps from what you would see is, as soon as the pump would lift off, the power would drop, and you would apply pressure over 0 to 300 millimeters. The power didn't change at all, and that is this classic idea of a hydrodynamic bearing. So I knew going in that these HeartMate 2 pumps bearing wear was not going to be the issue, because they were hydrodynamic. And indeed, that's the way. And I remember year after year at the ASAIO meeting, I kept saying, this is what we see. There's no bearing wear. There's no bearing wear. And even after we had patients go out a year, there was no bearing wear. We couldn't see it. And so a lot of the magnetic bearings concepts were founded because they were afraid these mechanical bearings would wear out. Well, they don't wear out. You got other problems, connectors and all the stuff that Mark talked about yesterday.
Well, certainly, the development of these devices, it's a difficult task, and there are a lot of ups and downs, and you need to be very persistent. But is there any big disappointment in your career in the development? Something that you were very disappointed didn't occur, or?
I can honestly say no. When I ran Nimbus, we had 2 rules: have fun and don't do anything stupid. And that really worked for me. I've had fun throughout this whole thing, and probably it was disappointing if those first in vivos in Europe went so bad. I mean, because they really were, this pump is not ready for prime time.
Right.
And I was deeply disturbed about that. And I do remember after we came up with a new version with the smooth surface being the first implant we did. Of course, Dr. Frazier did it down in Texas. And I remember being aware that it was happening. And we got some early information back that it wasn't working. We were having high power spikes. And I thought, oh God, I don't know. I don't know what we can do next. But we sent one of our guys down there, and he said, "That's bullshit. This thing is working perfectly." And it turned out it just worked like we said it was going to work. So I only say just except for those few months while we were making the changes, and I was under a lot of pressure from Thoratec to make sure that. I remember Keith telling me, "Damn it, Ken, you'll never stop engineering this thing. You got to stop." Right. I said, "Well, we need to do this." Okay, so there were times when it was a lot of pressure, but overall, I've been lucky.
Well, I think it probably takes more than luck, but certainly when you have something like that happen, it would be easy to just sort of say, well, let's just move on. But being persistent with it. What do you see for the future for heart assist or even total artificial heart? I mean, there's no really active program today to develop a completely implanted artificial heart, or NIH directed.
Right. No.
And also assist devices. Where do you?
Well, I think certainly the smaller they're getting. I mean, they have to get smaller, and I think the totally implanted system. I don't know, Gus. We've worked on these things for so long, and there's so much stuff that has to go to be implanted. I just think, I thought one time when all the interest was in tissue engineering, that maybe the long-term answer is, rural regenerative cells that eventually, but I am encouraged by the work that Leonard Golding is doing at the Cleveland Clinic with that rotary pump version of this Total Heart. I know Bud's been working with, I think he's using HeartMate 2s now, I don't know. Mm-hmm. But I think it's going to be, the Total Heart will eventually evolve to some sort of rotary pump, I think. I certainly, we've had a lot of experience with the pulsatile Total Heart, and it was a mechanical marvel, I think. I mean, we did some of our finest engineering in the carbon composite blood pumps and the platelet energy converters, the little gear pumps, but they were fun to do. But I think the secret to the Total Heart is going to be in these rotary things.
What about advice for young people? ASAIO has really made an effort over the past several years to get young people involved in bioengineering. And are there any advice or tips that you give?
Well, I think one of the things I found along the way, if you're going to get a bioengineering degree, you should get a degree, a Bachelor of Science degree in the basic engineering core first, electrical, mechanical, and then go on to get the biomedical master's degree or PhD. And I think it's still a fascinating field. I'm a little disappointed we don't have the NIH support that we had in those days. And maybe those days are gone forever, but it's so, I think the HeartMate 2 took like $85 million before, when you look at it, before it was all on 30 years and $85 million to develop. And that's a big chunk for anybody to undertake.
Yeah, I'm not sure if business looked at that today, a business plan, and looked at the investment and the return.
Yeah.
And certainly not venture capital.
No, it isn't.
Because of
It
the
isn't.
time.
It isn't.
Yeah. Well, you have additional comments about your career or ASAIO? Or?
Well, I certainly learned a lot. I was of an era when my first exposure to these national meetings was to the contractors conference that was started in, I think, 78. And in those days we had, there were those of us who were developing blood pumps, there were those of us who were developing energy converters, and they kind of left it up to NIH for each of us to seek each other out and work. And we were lucky that we were able to do some early work with Thoratec and Don Hill with our electrohydraulic energy converters. Then we got involved with Dr. Noze and the Cleveland Clinic. And I remember those days when the cast of characters included Noze and Dr. Kantrowitz and Jarvik and Bob Whalen and some of the barbs that used to go back and forth. Jack Norman was in there also, and it was, for a young guy looking at all this, I thought, wow, what a wonderful education to have lived through all that. And I did get it. I think I gave the Hastings lecture. And anyway, that was my privilege to go back through all those years and look at how all of the companies, what they were working on, who they merged with, and it's a fascinating evolution of MAP. And I don't know if ASAIO still has that presentation, but it's pretty. If you want to know kind of what was going on in those days, I would, if we can get it, or if anybody's interested, they can get a hold of me and I can give them that set of stuff. But and then lately it's been the ASAIO meetings that I've been able to participate in, both as guest lecturers and monitoring sessions, and I do appreciate all that, and certainly the wonderful array of people that I've had to come in contact and meet. And I've enjoyed coming back after being away for several years this week, and I've certainly met a lot of old friends.
Well, it's been a real pleasure knowing you throughout the years, a pleasure interviewing you, and you deserve certainly congratulations for a wonderful career and contributions to the field.
Okay, well, thank you, and I just think I do appreciate, again, this opportunity, and it did give me the opportunity to look back on my career and just say how lucky I've been to be around the right people and be on this one project that it really worked like we said it was going to work, and that's the biggest. And I did meet one of the last things I'd like to say is one of the patients I met down at Pleasanton her name was Amy, and she was a former HeartMate 1 patient, and she had this big device, and they replaced it with a HeartMate 2, and how grateful she was to me that this thing has allowed her to live a very normal life, and I think she went on to be transplanted, but that made a really good feeling to see that come from the patient. So that's made it all worthwhile.
Well, great. Well, thank you, Ken.
Well, thank you again, Gus. It's been a pleasure.